Okay, so let me see if I can give you some hints on this homework. So let's look at the first one here. So here we say discrete time Fourier series, determine the Fourier series coefficients for each of the following discrete time signals, which are periodic in n equals 8. So we're going to be using the 8th roots of unity. All right, so here we go. I'm going to grab this first one here. I'll start a new OneNote. And we'll grab it. All right, now the key to all of these problems is something that comes from the lecture. This relation here, the relation between the samples and the coefficients. All right, so let me grab this. This is for n equals 4, but we're going to do the same thing for n equals 8. So I should probably zoom this in a little bit more. Go to 100% is fine. Okay, and let me grab that other one. So insert screen clipping. So I want to set up a similar matrix equation for the n equals 8. All right. So here I'm going to have I'm going to have x0 up to x8 instead of x0 up to x0 up to x7. So let's get my drawing pen. So we're going to have x0 up to x7. And that's going to be equal to, now I'm going to write this, so this is going to be e to the j. Now I have 2 pi n over 8, so that's pi over 4. All right. And then this is going to be 0, and then that's going to be times 0. So these all correspond to the first root. In this case, it's the first 4th root of unity. For us, it's going to be the first 8th root of unity. The second one is going to be e to the j, pi over 4 times 1, times 0. And then here we're going to go e all the way up to e to the j. And then the last one, instead of 3, it's going to be 7. Right? Pi over 4 times 7, because I have 8 altogether, and this times 0. Okay. So that's the first row, and then here my coefficients I'm going to have are a0. These are the coefficients I want. Okay. Then the way these columns go down, the power or the root stays the same, so this is still j times 0, but this is now times 7. Okay. This becomes e to the j, and this pi over 4 times 1, and this is times 7. And this is going to be e to the j, pi over 4 times 7, times 7. Okay? Seems like a lot of writing, but in fact this matrix simplifies quite a bit, because you know that e to the j pi over 4, that's equal to, remember it's cos pi over 4 plus I sine pi over 4. So that's equal to, let's see, so this is square root of 2 over 2, so it's going to be the square root of 2 plus square root of 2i over 2. Now, rather than writing out e to the j pi over 4, or writing this out each time, I'm just going to create a symbol for e to the j pi over 4 that I'll use in my subsequent writing. So I'll just say, so we'll say let w equal e to the j pi over 4. Okay. Then my matrix is going to be equal to what? Well, the first column has e to the j pi over 4 times 0 times 0 up to 7. But pi over 4 times 0 is 0. So this is e to the j0 all the way down. So the first column is all 1s. The first row is also all 1s. In fact, the matrix is symmetric. So once you fill in the column, you also have the corresponding row. Right? So this is also all 1s. Let's look at the second column. Well, this first one is 0. Second one is going to be e to the j pi over 4 times 1. That's the same thing as what I'm calling w. So my second column is 1. I'm sorry. Yeah, that's right. Then I have w here. Okay. Then I get w squared. Now what's w squared? Well, look at the circle here. If I go around, this is w. W squared is in fact j. W cubed is here. So w cubed I could write as jw. Right? Because I'm going around j and then w. W to the fourth is minus 1. W to the fifth is minus w. W to the sixth is minus j. And then this one here is going to be minus jw. Okay. So that's what happens. 1 w. In fact, I can write the row here because the row is the same. It's 1 w j jw minus 1 minus w minus j and minus jw. Okay. And the column is going to be the same. J, and it goes down. The last one is minus jw. Okay. So you can write out this entire matrix. This last one, minus jw to the 7th power. I believe the last one here is going to be w. You can try that and see. But I'm pretty sure that's what it is because you're going to be going around backwards. Right. So that's what the matrix is. Now I want to get the a's from the x's. So I want to get the inverse matrix. Now I think I've been saying something that's not quite right. The inverse matrix is actually the complex conjugate. I said it was the transpose. That's not true. It's the complex conjugate. And you can get the complex conjugates from this picture, right? The complex conjugate the complex conjugate is still going to be 1s across the top, 1s down the first row, first column, but the complex conjugate of w is now minus jw. In fact, as you go forward, omega w, jw, j, jw, etc., the complex conjugates are going to go backwards. Right? The complex conjugate of j is minus jw. I'm sorry, the complex conjugate of j is minus j. The complex conjugate of jw is minus w. So I put a minus w here. The complex conjugate of minus 1 is minus 1. Okay. So then this goes like this. I'm just doing this row backwards. J and w. All right. So you only need to write down the inverse matrix once. Okay, and then you'll use it for all of the problems, right? Now let's look at the first problem here. What is my x? Well, why don't I just write it here? X of 0 is 0. That's good. I always like to see 0. X of 1 is 1 over root 2. X of 2 is 1. X of 3 is 1 over root 2. X of 4 is 0. And then I have the negatives. Negative 1 over root 2, negative 1, and negative 1 over root 2. So that's my x. Okay. So I'm going to be using this x to recover the a's. I'm going to multiply the inverse of this matrix times the x. So if I go down here, so I'm going to do the inverse matrix. So this is going to be 0, and this is 1 over root 2, and then this is 1, and this is going to be 1 over root 2 again, and then this was 0, and then this is negative 1 over root 2, and then negative 1, and negative 1 over root 2, and then 0, and then that's it. 1, 2, 3, 4, 5, 6, 7, 8. That's it. I need to multiply this by the inverse matrix. Okay, so the inverse matrix, well, here I had 1s all the way across the top. I can just do a couple of these. 1s across the top, and then this was 1s down. And if you remember, this was W, J, JW, minus 1, minus W, minus J, minus JW. And then this is going to be, that's it. Okay. All right. So what happens when I multiply these? When I multiply the 1s times this here? Well, here's where you have to start looking at patterns. Right? You can see that here I have positives, here I have negatives. So if I multiply by 1s, I'm going to get 0. The first one is going to be 0. So let's see if we can just do the second one. Now, you can see here that what we have here, these are positives, and these are the negatives, and these are the positives, and these are the negatives. So it's actually going to reinforce instead of canceling. So this second entry, let me call this A1, A2, because I don't have room to write it. So I'll write A1. A1 is going to be what? Well, it's 1 times 0. So here's where you want to find ways to simplify. It's going to be a W times 1 over square root of 2. So it's W over root 2. It's going to be plus J. And then here it's going to be JW over root 2. Sorry. Okay. And then we have 0 again. And notice that here I have the negative numbers multiplied by the negatives here. So I'm just going to get the same thing again. So I'll multiply it times 2. Okay. So what do I have here? I have 0. Here I have a J. So if I group things together, I have J plus, and here I have W plus JW. So it's 1 plus J over root 2 times W. Okay. Now, actually, 1 plus J over root 2 is equal to W. If you look at where that is, 1 plus J over root 2 is over here. It's on the unit circle, and it's in the same direction of W. So this is equal to J plus W squared. So this is equal to 2J. Okay. So just go through and do this kind of stuff, and you'll be finding all of these coefficients. They will be complex. Turns out that if this one is 2J, the last one is going to be minus 2J because it's going to be the complex conjugate. You can work that out, but it turns out an A2 will be the complex conjugate of A6 and so on. So you'll start seeing some patterns. All right? So this is the way to do it. And as you do this, you'll find more and more shortcuts, and you'll find more and more relationships. Okay? So that's how you can do these problems here. Okay? So let's go on to this next one. All right, now this one here. Determine the discrete time signals with the following Fourier series coefficients. Assume that the signals are periodic and n equals 8. Now here you simply go forward. Here we went backward from x to a. Now we want to go forward from a to x. Now one thing I'm sorry I made a mistake here, that the inverse matrix is not just this. The inverse matrix is 1 over 8 times this. Okay, so this is going to be 1 over 8. But the forward matrix is here. Okay, so for the second set of problems, I'll just grab one and show you. So we'll just use the forward matrix. So to get the x's from the u's, or x's from the a's. Now, before we had A0, A1 up to A7, but here he's giving it differently. He's doing negative and positive. But it doesn't really matter because I can continue this periodically. All right. So in this first case here, you can see I have A0 equals 1. Then A1 is 1 over square root of 2. Then A2 is 0. Then A3 is minus 1 over square root of 2. Then A4 is minus 1. Now it's going to repeat. You see that this was the same as this. Okay? So A5 is going to be this one. So A5 is equal to minus 1 over square root of 2. Okay? Then A6 is going to be 0. And then A7 is equal to 1 over square root of 2. Okay? So then I want to get the x's from x0 up to x7. It's going to be equal to the matrix, which is this is the forward matrix. That was the original matrix that I wrote down here. I didn't finish writing it down, but the original matrix up here, and multiply that by these values. Okay, so this is giving your complex multiplication a workout. Now, this impulsive input problem, quite probably he has a prettier way of doing this if you look in the answer key. But one way of doing this, if I just paste that here, straightforward way of doing this is just draw out what the signal is and apply the impulse response and figure out what the signal is. So x of t, if you look at what x of t is, he tells you it's periodic, and you can see the period is 3. So let's see what happens here. When t equals 0, you can see that you just pick up the delta here. So you're going to have a spike here. I suppose I should use a different color so it looks clearer. So you're just going to have the spike here. When t equals 1, that picks up this one here. So there's another plus. When t equals 2, you get a minus. So this signal is just plus, plus, minus, etc. But you're passing it through this. So what does this do? Well, we should figure out what h of t is. And if you look up the Laplace transform of e to the s over 4, I looked online, and you can also go to a table. It says that delta of t minus t0 goes to e to the minus st0. So what I have is e to the minus s pi over 4. So this is going to be, so there's going to be a sum of delta functions. Okay. So this one says delta of t minus t0. So in this case, it's going to be t plus 1/4. I think that's right. Let me check that. Yeah, because here in this case, my t0 is going to be minus 1/4. So you make this 1/4. So it's going to be delta of t plus 1/4 minus delta of t minus 1/4. Okay? So I have to apply this to each of these spikes here. So what's going to happen here? T plus 1/4, t minus 1/4. I'm going to need some more room here, so I'm going to make this bigger. I'm going to redraw this but make it bigger. Okay, because I have to mark off the fourths. So, all right, so let's mark off the fourths. 1/4, 2/4, 3/4, 1. 1/4, 2/4, 2. 1/4, 2/4, 3/4, 3. And that will be enough because I know it's periodic with period 3. Right? Now, what happens when I apply the delta of t plus 1/4 minus delta t minus 1/4 to this delta here? Well, this one spike is going to create two spikes, one positive and one negative. This spike is going to be to the left, this spike is going to be to the right. So that means that that positive spike creates two spikes, one to the left here, plus 1, and one to the right here, negative. Okay. Now, the second spike, so this is at 0, this is at 1. The second spike at 1 is going to create two spikes. Positive 1 to the left, and negative 1 to the right. Whoops, sorry. Positive 1 to the left, negative 1 to the right. Now, when I apply it to the last one, to this one at 2, it's going to reverse the sign, right? Because I'm applying the deltas to a negative number, so this is going to be negative 1 to the left, positive 1 to the right. Okay? Now, this is going to continue periodically. So 0 is the same as 3. So that means that here I'm also going to have a positive. So I've got a bunch of spikes. I've got these positive and negative spikes. Here at 1/4, this is going to be 3/4, 5/4, etc. Right? And these are either plus or minus 1. Okay. Now, to find the so you just want to apply the formula for Fourier series coefficients. Okay, it's on the interval from 0. So the on t for okay, so this is for t equals 3. Because it's periodic with period 3. Okay, and there is a formula AK equals something, and just apply that formula to here. Now remember that when you integrate something, for instance, if I integrate any function f of t times some delta of t minus a, right? And I integrate this over any interval that contains a. This is just going to give me f of a. The spike pulls out the value of the function at this point. So, for instance, if I integrate, I'm not exactly sure what cosine I'm going to be integrating, but I'm going to be integrating cosine or sine or exponential, complex exponential. I think we'll do the complex exponentials for. So it's going to be something like this: e to the I kt, and then this delta here is delta. It's actually going to be minus times minus delta, and this is, you're integrating here from 0 to 3. This is minus delta of t minus 1/4. That's just going to pick up the value of this function when t equals 1/4. So this is going to be e to the I k over 4. Okay, I don't know what your k is, but the k will come from the Fourier series formula. So you can look up this formula, apply the formula, and the integral, you're not actually going to have to do the integral. So when you do the integral, it's actually just finding the values of the complex exponential at these 1, 2, 3, 4, 5, 6 points. There's probably another way to do the problem, but that's one way. Right? And now this next problem, find the Fourier transform of this function. That's just going to be, just look up the Fourier transform integral. you're going to be integrating on two parts, from minus infinity to 0 and from 0 to infinity. Now for part B, I suspect that the result you get here is going to look something like 1 over 1 plus omega squared or something like that. Duality says that the Fourier transform of a function is equal to the conjugate of the Fourier inverse transform. Okay, so you can just look up duality and see how that works, but you shouldn't have to do another integral. If you can do this integral and you get an expression like this, to go backwards, you're just going to be taking complex conjugates. So you shouldn't have to evaluate two integrals here. Okay. Now this here, he kind of obscures the simplicity of this problem here. Here he says determine x of x1 of t where the Fourier transform has the following magnitude and angle. Basically, you want to change the magnitude and angle back into a complex number. All right. Now, it's pretty clear that the value of the function is 0 outside of minus 3 pi to 3 pi. The magnitude is linear, and the phase goes from pi over 2 to minus pi over 2. Now remember, if a complex number has phase pi over 2, then it's imaginary. When the phase is pi over 2, this is on the imaginary axis. This is on the negative imaginary axis. So basically, we want to take these two graphs and put them together to find out what the complex number x1 is. Okay, so I copy that over here. And so, whoops, no, I didn't copy it over there. Okay, where are we? All right, so I want to figure out what x1 of j omega is. Well, this is equal to the magnitude of x1 of j omega times e to the j times the angle of x1 j omega. Okay, so I'm going to use this graph to find the magnitude and this graph to find the phase. So the absolute value of x1 j omega is equal to, looks like it's just equal to the absolute value of j omega when omega is between minus 3 pi over 2 and 3 pi over 2. So when the absolute value of omega is less than or equal to 3 pi. Okay? And the phase is either equal to, so since the phase is pi over 2 or minus pi over 2, this part here this is either going to be j or minus j. It's going to be j when omega is greater than 0. It's going to be minus j when omega is less than 0. Okay. All right. So here, of course, absolute value of j omega is just equal to omega. Absolute value of omega. Okay. And So what's happening here? So my total result is equal to. So the total result is I have j absolute omega when omega is greater than 0, and minus j absolute omega when omega is less than 0. And of course, this is also having the absolute value is less than or equal to 3 pi. Okay. Now look, when omega is 0, when omega is positive, this is positive. When omega is negative, this is negative. So I can just take off the absolute value. So this is just equal to j omega for omega less than or equal to 3 pi. Okay? All right. Now, so I can just use this in my Fourier inverse transform formula. And you can do the same thing for the second one. What you want to do is take this second one and write this also as a function of omega, right? Take the magnitude and the phase and put that together into a single expression. Okay, number 6. This is one of those where you have some signal and he gives you the Fourier transform. And he wants to know, if you change the signal, how does the Fourier transform change? Right? Now, one way you can do this, if you look at these changes here, derivative, convolution, shift, multiply, x squared, if you go to the table, this is in the lecture. Which lecture is this? Lecture 16. There's a table of Fourier transforms. No, don't worry about the j omega here. You can just think of this as a function of omega. Right? So what does differentiation do to the Fourier transform? Well, it multiplies it by j omega, and then you have the same Fourier transform here. Right? So think about what this does to the magnitude and the phase of the Fourier transform. So if I pull out this line here, okay. So let's see what we can do here. Insert screen clipping. If I take this here, so I'm looking only at the first and last columns. The middle is the Laplace transform. So this is the derivative, and this was so the magnitude of the Fourier transform of the derivative is equal to the magnitude of j omega x. I just write this as omega here. Okay, same thing. And so it's equal to the magnitude of the omega times the magnitude of x of omega. Okay? So if you look at what the magnitude of omega looks like here, I think it was here, I'm going to be multiplying that by omega. Okay? Now, omega is 0 here, and it's 1 here. So you can imagine what happens if I take this magnitude and multiply by a function that goes from 0 to 1. And of course, the magnitude is the absolute value, so it's going to go 0 to 1 here, 0 to 1 here. So that's what it's going to do to the magnitude. Then you have to think about what it does to the phase. Okay? So what about the phase? Okay. Now remember, when you multiply, you add phases. So this is equal to, it's equal to the phase of j omega plus the phase
What's the phase of omega?
X.
Well,
right?
It's 0 when omega is positive, and it's pi when omega is negative, right? Because negative numbers have phase of pi. So you take the phase of x, add pi over 2, and for the positive values, you add 0. For the negative values, you add pi. Now, now pi is also minus pi. So if you go outside of the phase from minus pi to pi, you'll have to subtract pi instead of add pi. Okay, so that's how you get the phase. That's how the phase will change. Okay, have fun.